Moment. Yeah. Okay.
Ah, I see now that it's being streamed to YouTube. I got the
Yeah.
notification in the corner.
Yeah. Okay. All right. Okay. So that's appear. So once it disappear, I will say some words. Ok. Muy buenas tardes a todos los que están atendiendo esta exposición. La verdad que hoy día tenemos un grupo muy interesante y que nos conocimos durante el ICAS en Florencia, y me refiero a una temática que se va a presentar de quienes pertenecen a la DLR, que es el Centro Aeronáutico Alemán. En virtud de que nuestros invitados de hoy día hablan inglés y alemán y yo no hablo alemán, tengo que referirme ahora en inglés. Well, what I told you before when we were speaking before this talking, I have to introduce you since a long time ago, not long time ago, was just in September. Last September, we met in the ICAS in Florence, and you were one of the speakers. And just to clarify to our audience that the speaker could be able and are able to do so when they are selected, when you are chosen to do that, because all the committee just read and study all of the abstract, and the best are selected. So this is a very good recognition for you. So I'm glad that you could be in contact with us today. And I will introduce you who are behind us. So just to introduce you, sometime there's a system. They're the result of the entry to the DLR Design Challenge, a competition for students' teams in German universities. The goal of this year competition was to design a regional aircraft for 2050, zero carbon. That is the goal. The title of presentation, DLR Design Challenge 2024, Design of a Cost and Energy Efficient Regional Aircraft. Today we have Matthias Teckel, Bachelor of Science Transportation System from the Technical University of Berlin, 2021. And since 2022, studying in the master program MSc Aeronautics and Astronautics at the University of Berlin. And Tim Schulz, since 2024, is studying Master Science of Aeronautics and Astronautics at the University of Berlin. So you have the floor, and you can start whenever you want.
Wonderful. Let me just get my screen ready and share the presentation with you. Here it is. I hope you can see my screen right now.
Absolutely. Very good.
Wonderful. Okay, well, thanks for the brief introduction. Yes, I'm Tim Schulz, and I'm here with Matthias Teckel. And together with a few other fellow students, we participated in this year's DLR Design Challenge. Well, the DLR Design Challenge is an annual competition hosted by the DLR, the German Aerospace Center, and in which students compete against each other in various tasks, differing from, like, the first one shown on this picture was all about designing an urban airliner, and well, the winner called himself Urban Liner from the TU Munich. A few years later, they had to design a rural aircraft to transport 6 to 10 people to a little larger airports. A few years later, well, last year, the students had to design a drone to regain internet connection in catastrophic areas. And as just introduced, this year was all about regional and short-haul design, which brings us to our solution. Well, and before we start to design new aircraft, we actually had to figure out if there's any market for the aircraft. Well, as state of last year, the aviation industry is still kind of recovering from the previous COVID crisis, but will handle the challenge with ease. and is expected to reach about double the amount in revenue passenger kilometers by 2050 compared to last year, which is plenty of market for us and for aircraft. Leaves just the question, what market actually? Well, and one of our main focuses is climate change. And roughly 1/3 of all aviation emissions are emitted on short-haul and domestic flights, often covering less than 1,000 kilometers. That's about the range you can see over here on the map. Well, an example network for those ranges was provided by this year's DLR Design Challenge. And you might notice some of the routes are extending the just mentioned 1,000 kilometers by far. And well, northern Germany is quite rainy and dark, and the winter isn't that nice. So it's tempting to go into the south and the warm Italy. But it's kind of hard to design an aircraft for such a variation of ranges, which is why we were allowed to consider stopover flights, reducing the actual required range to about 900 kilometers. That's roughly the distance of Hamburg-Edinburgh. It's noticeable to say that for all those ranges and routes, the DLR provided within the task an amount of route demand and a minimum and maximum amount of takeoff slots and landing slots at the airports, which predetermined the aircraft to about 60 to 120 passengers. That's going to be important later on. But first, let's go back to the routes. And how are we going to fly those climate friendly?
Yeah, it's prognosed that by 2050 air travel will increase, and sadly also the greenhouse emissions will roughly double. So like one of the only sectors that by 2050 will actually have a growth in CO2. But the EU is trying to combat that. By 2050, the EU wants to use 70% of sustainable aviation fuels for air travel. There's a legislative act called the Refuel EU Act, and according to that act, only hydrogen and sustainable aviation fuels are considered CO2 neutral. But it's still only 70% of sustainable aviation fuels. And by 2050 and after that, commercial aviation in the EU wouldn't be exactly CO2 neutral. If you look at another energy carrier, namely electricity, it's prognosed that by 2050, up to 94% of energy generation in the EU would be renewable, so with a very low CO2 footprint. So it can be assumed that by 2050, electricity is a good source for CO2-free energy. But let's also look at the efficiencies of these energy carriers in more detail. In the assignment, we were given to use either SAF, hydrogen, or electricity. On the left side, it shows the total grid-to-shaft efficiency of these energy carriers. It's noticeable that sustainable aviation fuels have quite a low energy efficiency of up to 20%. Hydrogen is marginally better, but up to 30%. But battery electric is the most efficient with the 77% total efficiency. Also, when looking on the right side for the energy costs that were also given by us in the assignment, it's noticeable that battery electric is almost a third of the price of hydrogen. So in combination, it's an energy carrier that has a high efficiency and also a low cost. So we were also asking, what do we need for energy, for battery electric flight? What is actually technically necessary? So first, to answer that, we used the Bragg-Williams approximation formula to calculate the final MTOM of battery electric aircraft, depending on the usable specific energy of the batteries and also the empty mass fraction of the whole plane. On the left side, you see the 3D diagram of this. It's noticeable that at lower usable specific energies, the MTOM increases rapidly. This is explained simply because of the mass of the battery increases, and you have to compensate this increase with a further increase, and it's just a slippery slope. To combat this, we limited our design to 40 tons final MTOM and assumed that the empty mass fraction would be around 50%. From there, we deducted that the minimum usable specific energy for our battery packs should be 700 watt-hours per kilogram. And then the feasible empty mass fraction of the aircraft is at 50%. But let's look in more detail what battery technologies we can expect to use by 2050.
Well, as we just learned, a feasible electric aircraft requires at least 700 watt-hours per kilogram of specific energy in the battery pack. That translates to about 1100 watt-hours per kilogram of specific energy in the battery cell. And as you might see on the graph over here, we are far from those numbers right now. But the task wasn't to design an aircraft for today. It was for 2050. And by 2050, the outlook is quite different. Well, for once, there's lithium sulfur. Those batteries aren't far enough developed by 2050 for our aircraft. But there's another alternative, lithium air. Those batteries bind oxygen from the surrounding air while emitting energy and are expected to reach up to 1400 watt-hours per kilogram of specific energy in the battery cell by 2050, which is far more than we require for feasible battery electric aircraft. So to come back to Matthias' question from before, what is necessary for a battery electric aircraft? Lithium air batteries, and they will be there by 2050. So this is why I can introduce charge. Oh, I'm sorry. So I think now you should. Charge is our carbon neutral, high efficiency aircraft for regional electric flight. The marvelous design is characterized by a futuristic looking box wing, which on one hand provides an excellent in-flight efficiency, but on the other hand, keeping the wingspan quite low. Along the wing's edges, spread out 20 propellers, providing us with distributed electric propulsion, which leads to a maximized energy efficiency, even during climb and approach, which we do quite steep to reduce noise emissions as far as possible. And since we're using electrical motors, they don't require much maintenance and can cut some costs in this department. Strapped to the wing is our fuselage, built with a sandwich composite structure, which is ultra lightweight and preserves a lot of resources. And if technology is ready by 2050, we are opting to enhance or even substitute as many carbon fibers with natural fibers as possible to reduce waste, further reduce emissions, and protect the environment as much as we can. But those are just some empty words. We're ongoing engineers. Of course, we calculated why charge is so ideal for its use case.
So, as mentioned before, we were not given a specific configuration for the aircraft, but rather a route network and the amount of passengers we had to serve. And based on that, we could have a configuration between 60 or 120 passengers in each plane. The question was, how do we calculate the perfect design for this design mission? So for that, we developed a complex iteration process where each abreast and passenger configuration was actually calculated. So each configuration in the plot shown here is actually a valid aircraft design. We also developed a scoring system to to score the configuration. And we weighed energy consumption with 70% and the seat kilometer cost by 30%. And in the final configuration that was most efficient was 110 passenger configuration using the indirect flight network. It's also noticeable that there are two trends on these on this chart. Firstly, with the increase in passenger numbers, the scoring gets better as the aircraft is more energy efficient per passenger kilometer. It's also noticeable that all the indirect flight configurations with the max range of 894 kilometers have a way better scoring than the direct flight networks. This can be explained by the increase of the battery mass that's required to fly the 1,400 kilometers compared to the 894 kilometers. Let's have a look how the airplane configuration looks like in detail. So here it is shown a cross-section of the aircraft in 5 abreast, 3+2 seating order. In total, it can carry 110 passengers, and it has a capability for single pilot operations. So we only need one pilot at the front. In the cabin, the aircraft would have 3 crew members to assist the passengers during their flight or in any emergency cases. Otherwise, it's quite a conventional commercial aircraft with a few galleys and a few bathrooms at the front and back. But let's also look at the outside dimensions. So because of the box wing design, we were able to limit the wingspan to 28 meters. And the aircraft is in the ICAO Aerodrome Category C, which is very useful for our flight network as we have to service smaller regional airports. Otherwise, the aircraft is roughly 31 meters long and just under 8 meters tall. When we look in more detail of the mass of the aircraft, we see that we did reach our goal of staying under 40,000 mTOM as we tried to during our feasibility study with the Breguet approximation. And only a fourth of the aircraft final mass is actually the battery with roughly 9 tons. Interestingly, we also stayed at 50% operating empty mass, which we also assumed in our first approximations. But let's look in more detail in the batteries. Well, the batteries have a total energy density on the back level of 1,200 watt-hours per kilogram. But if we consider depth of discharge protection and degradation, the usable energy density is 720 watt-hours per kilogram, above the minimum that's feasible for an electric aircraft design. The lithium-air batteries are divided into 4 battery packs under the floor of the cabin, and they can be easily removed by openings on the steerboard side. They can be charged over 4 charging ports, so each pack is charged individually. And for the maximum range of 900 kilometers, it only takes 26 minutes to charge them. The batteries themselves are quite safe as they cannot self-inflame, but each pack is still self-contained and also has an extinguishing system in case of emergencies. We also took into consideration that every 1,500 full cycles, the batteries have to be exchanged as their charge holding capability falls below the requirement to fly the aircraft in longer ranges. But this is not a considerable issue as they can be changed every 23 months during overall C-check of the aircraft and doesn't have any operational issues. Furthermore, after the 1,500 cycles, the batteries aren't worthless. They can still be used in second life applications like in the automotive industry or in the energy industry. Now let's also look how the batteries and the electric motors are connected to one another.
Well, as we just learned, our aircraft has 4 battery packs, and they somehow have to be connected to the motors. We can't just put a cable through the aircraft body and hope it will work. So we had to figure out a lightweight and redundant way to do so, which is why we applied a 3-bus multi-feeder architecture, looking about like this, which is very overwhelming since there are a lot of cables, lines, points, buses. So I tried to simplify it a little, which would make it look like this. Right now, we're assuming there's just one motor per wing, and let's see how it's redundant. Right now, every battery pack is powering its motors, since there are 4 wings, 4 batteries, 4 motors. It works this way. But let's just assume one battery fails. It's highly unlikely, but let's have a look. Even if a battery fails, you would still be able to operate all 20 motors on full power. And in this configuration, we could even say the center bus fails as well, and we would still be able to operate charge regardless the damage, which makes us very redundant. But let's have a look at charge operation. Well, while flying throughout Europe, since that was our task given by the DLR, with about 900 kilometers of range, we had to overcome some obstacles like the Alps, which is why we chose an initial cruise altitude of about 7.5 kilometers and a cruise speed of Mach 0.57. On the ground, we're taking off in just short over 1400 meters, thanks to the installed power of 6.24 megawatts, which enables us to operate even from the smaller airports, like the regional ones we had to operate from. And as just mentioned, our charging time is in about 12 to 26 minutes, depending on the before flown range. But let's have an even closer look at Charge's mission. Well, at first, we bought the aircraft. So fast and efficient, thanks to the built-in air stairs, we already missed it and we're pushing back. Thanks to the built-in front wheel motor on our own. So right now, we're completely independent from airport infrastructure. After pushback and taxiing, we take off. Because of our distributed electric propulsion in no time and very steep to reduce noise emissions as far as possible. In the air, we're very efficient. Economically, thanks to the single pilot operation, and ecologically, thanks to the very efficient box wing and the morphing trim rudder section right in between the V-tail. After flying, even though it was very nice, somewhere we have to land, we land, of course. Again, very steep to reduce noise emissions as far as possible. After that, we taxi back to the gate or airfield position, and while boarding, of course, we charge, which is a huge advantage of battery electric flying compared to other energy sources. But again, those are just some words about Charge's mission. Let's have a look at some numbers.
So to fill our passenger requirements in the network given, we need 4 planes in total to cover the whole network. On average, 102 passengers are transported in each plane, which is over 90% of a fulfillment rate of the 110 passenger in total. 90% of the time, the aircraft are utilized, which leaves a nice margin for any delays. If you look in more detail, the seat kilometer costs of the aircraft, then the average seat kilometer cost is just over $7. Very noticeable in this diagram is that the energy costs are only at 3%. This is explained by the quite low energy cost for the electricity we were given, and also the high efficiency of our aircraft. Also, the crew costs are slightly reduced thanks to the single pilot operation capabilities. But let's look more in advance in the energy consumption, which was one of the main criteria for our aircraft design. Well, this is at 51 watt-hours per passenger kilometer, which is considerably lower than comparable aircraft like the Dash 8, which uses over 6 times more energy than Charge would when looking at the energy equivalent. We were also curious, how does our aircraft configuration compare to other transport systems, like fast trains or electric cars? Well, even in this case, the aircraft uses less energy per passenger kilometer than an electric train and almost 3 times less than an electric car. This is partly also explained due to the higher usage rate of the aircraft compared to trains and cars, which are sometimes only half filled. We were also looking at how does this compare time-wise to trains and cars. If we look at one of our connections in the network, Hamburg-Munich, which is roughly 600 kilometers from the north of Germany to the south of Germany, our plane could do that connection in slightly over an hour, while the train would take 5 over 5 hours, and the car roughly 7 hours, if there aren't any traffic jams or delays. So if you would summarize our concept, we have shown that battery electric flight is by 2050, at least in Europe, the only true zero-emission commercial flight option. All of the other options, hydrogen or SAF, would probably have a higher CO2 footprint. But to achieve this, we need a highly efficient design, which is possible with the box wing and distributed electric propulsion. Even though it might sound expensive to build a battery electric aircraft that only flies 900 kilometers, we have shown that due to the high efficiency and ease of operations of our configuration, it's also economical compared to other aircraft in its class, or even aircraft like the Dash 8 nowadays. So yeah, this was our design, and we were very glad we were able to present it.
Well, of course, we weren't perfect. There's some considerations and flaws we saw later on. For example, on this graph, we noticed we could, of course, shift the graph a little to the left, for example, to further increase efficiency, especially cost-wise, since our average network utilization isn't at the optimum, and there could be made some gains. As well as the box swing concept in general is kind of hard to design flight mechanical-wise, as well as it's not able to stretch or shrink the aircraft because of those weird flight mechanics and hard to design. And at last, because the batteries take off a lot of space, there isn't any room left for luggage, which wasn't given by the DLR, but well, short regional flights often transport the people, which then go on long flights and long haul flights. And for those flights, you need luggage and big luggage. There's no space for charge right now. There's no space on charge for that right now. Of course, you could like argument in the future, if as the batteries get more dense, the battery energy gets more dense, there could be some room for those luggage compartments, while keeping the range of charge the same. But that's something we haven't looked at, and that would be something for the future. Yeah. Well, thanks for listening. One last picture of the whole group behind charge. The other four weren't able to attend today. And yeah, I hope you enjoyed it.
Well, quite much, Tim and Matthias. And before we have maybe some questions from the audience, thank you so much for your time, because this is the future, definitely.
Mhm.
We can maybe discuss about when we will have the technology, but definitely if we want zero emission, that is a fact. Yeah. And well, I have some questions. While I expect that some others will ask another. Maybe I missed some slide, but how about the ECS consumption? Because normally when you are fully electrified, let's say in a car, you need let's say to heat the air in order to have a good let's say air conditioning for winter, for example. So what is the let's say the effect of the ECS system in the life of the batteries, because you are consuming, of course, for the motors and then for the ECS as well. So what is the calculation?
So what we proposed in our design was that we use combined system of an ECS and TMS. So TMS we call thermal management system, and because we have the motors themselves are actually highly efficient. They're like 99% efficiency, and they don't need much cooling per se. They would be air cooled by the oncoming air, but we do need to cool some of the electronics and also have to cool or preheat the batteries depending if you want to charge them, decharge them. So what we proposed was that the heat left over from the batteries or for the electronic systems would also be moved into the DCS systems to then keep the cabin at least warm during cruise height. But to dimension the ECS systems, we did derive a power requirement for them. We used, I think, the data from the 787, as it's a more electric aircraft and actually has an electric ECS and not the bleed air system. And from that, I think we derived that for this 900-kilometer range, around up to 3 to 5% of the total energy in the batteries is actually used to condition the cabin and use all of the other electric systems on board. And that we also used to then finally dimension the batteries themselves. So there was like actually a slight increase of the battery mass because we had to consider the ECS system.
Okay. On the other hand, you mentioned that for a while, you don't have room for the luggage. How close? So, the passenger will kill us if we have an aircraft without a backpack. Well, maybe a backpack like that.
Yeah, there are overhead compartments. I think you saw it in the video. I don't have a picture of it right now, but there are overhead compartments, and we planned those. But there's no room in the belly for like big luggages, big bags.
Okay. So Ryanair and EasyJet are it will be very,
they are very happy.
They are very happy for that stream.
Yeah, for the audience that I can tell them that they are very constrained with the luggage. So today, I think Ryanair is the most, let's say, tough in that. A very small backpack you can carry on. And beside, another question is about the engine. You normally, and we have seen many design that includes many motors, electric motors, not only a couple of big ones. What is the iteration that, let's say, tell you that it's better to mount many electric engines instead of maybe 2 or 3, 4? So what is the, is that a structural, what is the main explanation for that?
Well, it's okay, you tell.
Yeah, in this case, so we were also searching for literature for high efficiency electric engines for aviation uses. And what we saw in the literature was that until 2050, until this time frame, it's very likely that lower power, so the maximum power of these very high efficient electric motors wouldn't be enough to just use 2 or 4. So that was one requirement. And then we were thinking, okay, if we have to use smaller ones, why don't we try to use in a distributed electric propulsion configuration, which during the starting phase, because of the high thrust of the engines, would actually help the aircraft achieve a higher angle of attack to take off. So because we also have this steep climb and steep descent requirements for lower noise emissions. So we were trying to combine those two effects. There's also like some research that using distributed it's possible to reach a CL max 0 when using a good flap system that we also considered an aircraft. So that is like that's one of the thinking about it, to use the small engines which are more efficient and combine them in a way that makes the aerodynamic of the wings even more efficient.
Okay, great. Another question from the audience. If batteries can't reach 1400 watt-hour per kilogram by 2050, let's say it reaches 900, do you think it will still be feasible to make electric regional planes?
Well, I think it's kind of hard. But I think we started calculating the aircraft with about 900 watt-hours per kilogram. But as you can see here on the Breguet equation, for 900, we would either have to go on quite unrealistic empty mass fractions, or consider a higher MTOM. And with a higher MTOM, we need more batteries, and it's a down cycle. So it's going to be hard with 900 watt-hours. I think we need at least 1,000 to 1,100. With less, you would have to work with range extenders since the divert ranges are so huge that it's hard for the batteries to do this. There could be some ways like you could consider if you have to divert, to go into the depth of discharge, which could give you 20% more battery capacity, which we didn't consider. We would have never touched those last 40%. So it could go into the direction, I'm not sure. But yeah, I think 900 is the border where you would have to start to work with range extenders and SAFs.
Okay, thank you. Another question. Many thanks to Matthias and team for the excellent work and interesting project. My question, from a flight safety perspective, what risk have you been able to identify in advance in the flight of an aircraft like this, which integrates many cutting-edge concepts, and how could they be mitigated?
That's a good one, because I think we have like two main concepts in the safety aspect. So one, we have the single pilot operations, which is even nowadays very hardly discussed in the aviation sector, in the commercial aviation sector, if it's even legally possible to do it, even in the future, even though technically it might be. In our case, even if it's a dual pilot operation, wouldn't be a killer for this concept. And another thing we have is I guess the whole electronic system, including the batteries. So we do assume that by 2050, the lithium-air batteries, which are now still in the laboratory tables, would be usable and also safely usable. They do have advantages compared to lithium-ion. And then also the whole issue with the high power electronics that would be necessary for electric aircraft. These are components that haven't been developed yet, because there's no need for commercial aviation for that yet. And they would also have to be strictly tested because of the high voltages or high currents and high powers that would have to go through the whole system. And I guess this is also one of the things we saw in our technology readiness level research, that according with the batteries has a quite low readiness level nowadays. The other options, fiber composite fuselage, is not that high tech. They're like the A350 has that. Airbus is doing research with thermoplastics. And then I guess the box wing, and specifically the control system for the box wing, applied mechanically, would also be interesting, difficult to design, to have a configuration that's always in a stable flight, as this wing configuration has its peculiarities when you're dealing with stability, either dynamically or just mechanically.
Okay, right, great. Indeed, it's a very interesting project. And knowing what is the situation by now, how do you think a foreign country, foreign industries out of Europe, I'm going out of Europe for practical reasons, can participate in this kind of project? There is something just for European countries, some agreement. I ask you this because in the United States, they are putting about $1 billion to fund projects like this, NASA and the government. So my question is that.
Difficult one, because you're right that the DLR, it's very German specific. This competition was only for German universities. There used to be one 10 years ago that was together with NASA, but they stopped it. And otherwise, for universities outside of Europe, I think like one option, what is common in German universities, I don't know for others, is that students themselves come together and they form a group or a research group, and then with the help of the university faculties, the university let's say personnel, they're able to then do their own small aircrafts or drones and stuff like that, and research topics like this, or do flight mechanics, flight control research. That's something we also have in our university. It's like smaller student projects that then come together. They get some financial aid from the university, but they also ask for companies for sponsorships, and then do these stuff themselves, and then also write papers about it, or also get some credits for it.
Okay, it's gonna be very, very tough because okay, we are pretty far from Europe. So, and to get the fund to make a research and then to contact you, but you don't see any problem to, let's say, to have some kind of partnership with DLR from other universities in Chile?
No, I think it should work great.
I don't know. The DLR it's an interesting institute. It's state-owned and they do a lot of their own research. Like even with our university in Technical University of Berlin, don't have that many cooperation projects together with the DLR. The DLR is more very focused with towards the industry, in my understanding. They do a lot together with Airbus and other European manufacturers. So yeah.
Yeah, you're pretty close. Just yeah, in an hour you cross almost all Europe. Well, indeed, I don't have more question. This let's say a session will be recorded, so I will send to you later the links. Not that you have it. This is for sharing, so there is any problem with that. So again, thank you so much for your time. You are next to 8 p.m. in Berlin, I think so.
It's
If I'm not
about
wrong.
5 right now.
No,
Oh,
around
okay. Yeah, okay. All right. So again, Matthias and Tim, really appreciate your time because this is the problem that we have now projected to the 2050, and I hope we will have some solution concerning that decarbonization. So again, have a wonderful day, and thank you so much for your attendance, and I hope to see you in the future. So
Yeah, I
we
hope
can
so as well.
create
Thanks for having us.
a link. Okay. Thanks so much, and have a good evening.
Thank you
Thank
too.
you.
Bye.
Bye.
Bye-bye. Bye, team. Bye, Matthias.